Hello, I'm Edward Tarte, math teacher. This is one in a series of solution videos to some of my math challenges. The math challenge for this video is my Another Digit That Moved challenge. And here's how I presented that challenge in the original video. This is a follow-up to an earlier challenge which I entitled The Digit That Moved. In that challenge, we had a 6-digit number. We multiply it by 5/4, and what happens is the digit at the extreme left simply moves to the extreme right, with the other 5 digits staying the same. A bunch of you solved this. This new challenge is harder than this previous one, and my suggestion is that if you haven't yet investigated this one, that you look into it before trying this new one. Well, that was the old challenge. Here's the new one. The reason it's harder is that in that old one we definitely had a 6-digit number. In this one, I don't tell you how many digits are involved. We have a counting number of unrevealed length. We do as we did in the other one, we multiply it by 5/4. In this one, instead of the digit on the left moving to the right, the digit on the right moves to the left, while this unspecified length block of digits stays the same. What is this number? Here is my solution to this, one of my most difficult math challenges. We don't know how many digits the original number has. I will say it has n plus 1 digits, and I will name those digits from left to right: an minus 1, an minus 2, an minus 3, and so on, down to approaching the right end, a3, a2, a1, and the ones digit simply a. That digit a is the digit that will move from the right end to the left end. So I need an equation which says that the value of the original number times 5/4 equals the value of the new number. And here is that equation. Using powers of 10 to designate the different place values. 10 to the n power times an plus 10 to the n minus 1 power times an minus 1 plus 10 to the n minus 2 power times an minus 2 plus, and so on, then approaching the right end, plus 10 to the third power times a3 plus 10 to the second power times a2 plus 10 to the first power times a1 plus that ones digit a. All of that value multiplied by 5/4 gives us the new number, in which that ones digit a is moved to the extreme left, and so we have 10 to the n power times a plus 10 to the n minus 1 power times a to the n, plus 10 to the n minus 2 power times a n minus 1, plus 10 to the n minus 3 power times a n minus 2, and so on, plus, approaching the right end of the new number, 10 to the second power times a3, plus 10 to the first power times a2, plus a1. Now I take that equation and multiply it by 4, which will get rid of that denominator 4, and in the same step I will distribute that numerator 5 to the expression in parentheses on the left side. So my new equation is 5 times that expression in parentheses equals 4 times the right side of that first equation. Now if we get on the left side the terms containing a with those subscripts, from AN down to A1, and on the right side we get A without the subscript with its coefficient, with its multiplier. We get this equation, 46 times that expression in parentheses that you see equals 4 times 10 to the nth power minus 5 times A. And because 46 happens to be 23 times 2, I simply rewrite it that way. 23 times 2 times that same expression in parentheses from the previous equation equals that right side, 4 times 10 to the n power minus 5 times A. I then divide both sides of this equation by 23 times 2, and I get this new equation, 10 to the n minus 1 power times an, and so on, equals that expression in parentheses times A. That's over 23 times 2. That's 4 times 10 to the n power minus 5, that times A, over 23 times 2. The left side of this equation is place values with powers of 10. Looking at the right side, A is a single digit, therefore it is not a multiple of 23. Therefore the expression in parentheses must be a multiple of 23. And A must be a multiple of 2. A could be 2, 4, 6, or 8. A could equal 2. Let us assume that A is 2. We now focus on the multiplier with A, that expression in parentheses, 4 times 10 to the n power minus 5. We have established that it must be a multiple of 23. We do not know the value of n. If n were 1, the value of that would be 35. For n equals 2, its value is 395. For n equals 3, it's 3995. For n equals 4, it's 39995. For n equals 5, it's 399995, and so on. It's a 3 followed by a string of 9s and ending with 5. None of the numbers I've listed here is a multiple of 23. We need to find a number like this that is a multiple of 23. When we divide by 23, we keep getting remainders. What remainder do we need in order to put that final 5 on the end? Well, 23 times 5 is 115. That's 115. If we would get a remainder of 1, that's 11, then we could bring down the 5 and bring an end to this division. So, we need to divide 23 into a 3 followed by a string of 9s until we get a remainder of 11, and then we bring down the final 5 and conclude the division. Here is the result of that division. The numbers in that quotient, 1, 7, 3, 9, and so on, are the numbers that go in the place values of the original number beginning at the extreme left. A equals 2, we set A equal to 2, that is the number in the ones place. And so I have copied the quotient, putting a 2 on the end, and this is a number that satisfies the challenge. And indeed, if you multiply this number by 5 and then divide that answer by 4, you will get a 2 at the front, and then all the rest of those numerals in order from left to right following the 2. we set a equal to 2. We said earlier that a could equal 2, 4, 6, or 8. It's possible to work out other solutions to this challenge by setting a equal to 4 or 6 or 8, but I'm going to leave it at this, having set a equal to 2. And so that is my solution to my math challenge, Another Digit That Moved. Thank you for watching this solution video.